Okay, so you should have been working on your quizzes. You need to make sure all quizzes that are available to you are done by next Thursday and done to what you want to have for a grade on them. We are going to do today a review on nuclear, and as you came in, you picked up a paper that will help you to do the review. We are going to do that paper together, even though it says it's an assignment. I'm going to use it as notes. And then in the packet that you received with this unit, there is a review for nuclear. It's assignment number 4, and that's what you'll have for your assignment for today. Okay, so starting, let me see if I can make this bigger for you really quickly. Use the whole screen. Okay, so first of all, let's go back up to the top. We're reviewing nuclear chemistry. What is meant by radioactivity and radioactive decay? Anybody have any ideas? How would you define radioactivity and how would you define radioactive decay? They're two different things. They're related. They're two different things. Emily, put it away, please. How would you define them? We've been working with it for a while now, over a month almost. How would you define them? What is radioactivity? Yeah, we're going to use that as notes. So, and then your packet has a review assignment in it. So I'm just reviewing really quick the nuclear. So we're going to do this together. So you have another set of notes. So radioactivity means that I'm either going to get alpha or beta or gamma or some kind of particle off. Okay? Radioactivity means I'm going to somehow have some particle coming off. Radioactive decay, well, radioactivity can also mean I'm bombarding. So either I'm bombarding or I'm decaying. Because I can take and bombard something with neutrons like they do to start the nuclear reaction in a power plant, or I can actually use something that is unstable, that decays, to do x-rays and stuff like that. Yes?
Sorry, is this just a match?
Yeah, is it not?
Yeah, the first question is, why is it important that radioactive isotopes have used for nuclear?
I grabbed the wrong one then. Let me put the other one up then. Sorry.
Good things.
No. Okay, we'll get there.
Maybe.
So it's not that one, right?
No. I think the next question should be a patient who's administered
Probably
iodine 131. How much of
One.
this isotope will remain in the body after 40 days? Half-life for iodine 31 is 8.
You know what the easiest way for me to do is just come back here and get the same one you've got.
That also works.
Okay, let's just do this.
Get your own notes.
Yep. All right, try again. Thought I'd printed the right one. Evidently I hadn't for me because I wanted it one side. Nope. It's all right. I just was going to go with pencils instead so it didn't bleed through the other side.
That's what I often
Okay, so why is it important radioisotopes are used, when we use them internally, are short-lived? So you go to the hospital, they give you something to drink, and then they take some x-rays.
So it doesn't cause
Yes?
Can it detect issues, or no? Can't you take pictures of it or whatever as the isotopes are going through here so they can see the problems?
Right. So that's why we use it. But why do we want to have short half-life?
You don't want it in for a long time.
Right. If you have it around too long, then you're radioactive, which is what Emily said up here at the first. But he had raised his hand. So we don't want, why is it important? We don't want it to stay around long. So don't want it to be around long. And that does not show up very good up there, does it? Okay. We're going to go back to the other, and I'll just have to go get another one. Okay. So now here we have a patient, and it's been administered, it's okay, 20 milligrams of iodine 30. How much of this isotope will remain in the body after 40 days when the half-life is 8 days? So if we remember, we had two equations. We had A is equal to AO times 1/2 to the n power, and we had T is equal to T 1/2 times n. Now, n was a number of half-lives, T half was the half-life, and AO was the amount original, and A was how much did I have left. So we're looking, because they want to know how much will remain, we're looking for A. Here is AO. This is the total time, and this is T 1/2. So which equation do I need to use first?
Wait, what's next to the 1/2 on AO?
On AO,
Yeah, right, like above
Right here?
the 1/2. Yeah.
n, lowercase n. So we have everything we need for this equation right here. T equals T 1/2. We only don't have n, so we're going to solve for n. So n is equal to T divided by T 1/2. So we're going to take 40 and divide it by 8. What should we get? 5, yeah. Okay, so then we're going to take that and we're going to take the 20 and we're going to basically divide it in half 5 times. That's plugging in for the A equation. So 20 divided by 2 once is 10, divided by 2 again is 5, divided by 2 again is 2.5, divided again by 5 is 1.25, divided by again by 5, oh my goodness. 5, 6 something. Somebody's got a calculator. One more time. 0.625. I was close. Okay, that's how many grams is going to be left. So basically, we can just put that in our calculator. 20 times, in parentheses, 2 to the 1/2 to the 5th power, close parentheses. Okay, or we can take 2 to the 5th power and divide it by 20 divided by 2 to the 5th power. Okay, so that's how that works. So fusion reactions produce an enormous amount of energy. Why is fusion not used to generate electricity? Yes?
Because it doesn't last very long.
Oh, it lasts a long time. So fusion is what happens in the sun. Fusion is what happens when we have nuclear bombs. So try to contain that. That's the problem. It's too hard to contain. Try to contain the energy in a nuclear bomb in a building after you've set it off. Yeah, so the problem here is containment. Because it has so much energy, it just is too hard to contain.
So is it too cold for them?
So at one point, the U of U thought they could do what they call cold fusion, keep it so cold that they could contain that energy. But it was, they couldn't replicate it. Okay, so now I'm working in the hospital and I'm wearing a film badge. What's the purpose of the film badge? Okay, does it protect us from the radiation? That's one of the, what he suggested.
No, it helps to look inside your body.
Help to look inside their body.
I don't know, protect vital organs.
What does a film badge do for those that are working in X-ray? It's usually a name badge with underneath it has just like a sort of like a Roy G. Biv thing that sort of fills up when you are exposed to X-rays, or radiation. So a film badge basically tells me if I've had too much radiation and I have to stop. So if you're at the hospital and you're not doing stuff correctly and you're working in the X-ray, your film badge is going to light up, or it's going to show that you've been exposed too much. So that's the purpose of it. So you can quantitatively, how do we want to put that? You can tell how much radiation you've been exposed to.
So do people who work with radiation, do they develop any problems or anything?
They can if they don't do what they're supposed to. So oftentimes the X-ray technician will come in, get you situated, put lead over parts that aren't going to be exposed, and then they'll run behind a cement barrier and a lead-lined glass. So that'll protect them from radiation. But if they stayed out when they did it, then they're exposed to more radiation. So they're allowed certain amounts. We're all exposed to radiation daily. So they're allowed a certain amount, but above that amount, it can cause cancers, it can cause all kinds of things. So if a person has a film badge that has been exposed, then that person has to take so many days off without pay. So they're incentivized to not have their film badge go bad, but it's for their own health.
So can you still get sick if you're exposed to really minor amounts of it? Maybe not dangerous, but over time if you're exposed to little bits,
Anytime you're exposed to the sun and you get a sunburn, you've been exposed to radiation. So if you have sunburn over and over and over again, yeah, that causes skin cancers. Okay?
so is it more of a risky job, unless people want to do it?
Not if you follow the rules. If you follow the rules and do what you're supposed to do, then no. But if you become complacent and don't follow the rules exactly as you should, yeah, you can cause a lot of problems to yourself. So just, especially even us, if we go out and we get sunburned and over again when you're young, when you get older, the chance of skin cancer almost 40 times. So I have two sisters that are really they would go out they would go out and get sun tanned all the time when we were in high school. Well, now they're paying the price because they've had skin cancer taken off their bodies in several different areas. My sister that's just younger than me, just this last week, had 2 big pieces taken out of her face because of skin cancer. It doesn't show up right away, and yeah, that tan looks good, but in the long run, your body can't deal with it. Okay, so let's go down.
And I burn.
I burn too. Okay, let's go down to this one. I'm going to rewrite this so that we can see it a little bit better. So we're going to do the equation for 9038 strontium going through a beta decay. So you need to be able to do these equations backwards and forwards. Just remember that the arrow is the equal sign. Okay? So what is a beta?
Negative.
0, -1. And we can put an E or we can put the beta symbol there, whichever you would like to. Then I know I'm going to have to add something else. So as I've been correcting things and seeing things coming in, these are the easy questions, guys. This is not hard. 90 equals 0 plus what? 90. 38 equals -1 plus what number? 39. What number on the periodic table is 39? What element? Yttrium. Done. Okay, why? It's down in the D on the left-hand side. So let's do 14,6 carbon. How's it going to decay? Again, 0, -1, and it's an E plus, what am I going to get?
Wait, are they all 0 negative?
Well, we're going to change it up. I'm going to switch halfway through. Okay, so what do I get on this other side? Top? So 14 equals 0 plus 14, and 6 equals -1 plus 7, and 7 is nitrogen. Okay, now we're going to say that it now has an alpha decay at this point. So I'm going to switch it up a little bit. So if I have 13755 cesium, and it undergoes an alpha decay, what is alpha?
Plus 1.
4,2 what? Helium. So this is what an alpha is 4,2 helium. Okay, so 137 is equal to 4 plus what number? 133, good. So 133 plus 4 is 137. 55 is equal to 2 plus 53. And what's 53 on the periodic table? Iodine. Okay. We're going to do one more here. 239.93 neptunium gives, if we do an alpha decay again, it's going to be 4,2 helium, right? Plus what number? So 239 is equal to 4 plus 235. 93 is equal to 2 plus 91 is protactinium, so Pa. Now I'm going to change it up again. I'm going to do an electron capture. Okay, so if I'm going to do an electron capture, I have 5022 Ti. What is an electron capture? So I'm capturing it, so it's going to go on the reactant side, right? Plus, and it's a beta. So you're just going to do 0, -1, E. So I'm capturing a beta. Okay? And then I'm going to put the arrow, or the yield thing. So 50 plus 0 is 50. 22 minus 1 is 21. 21 on the periodic table is scandium. Okay? So you should be able to do any of these that I ask. So if it's decay, it goes on, the arrow points to it. If it's capture or bombard, so I'm going to also put bombard here. It goes on the reactant side. Okay? Decay or emit, product side. So decay or emit, product side. All right, so what's the difference between nuclear reactions taking place in the sun and nuclear reactions taking place in a nuclear reactor?
Sun is safe enough to a point.
So what kind is happening in the sun and what's happening in the nuclear reactor? Different kinds of reactions. What's happening in the sun? So which one's which? Fusion is the sun. Remember, fusion is the one we're having a hard time controlling. But fission is a nuclear reaction. So fission is like a fissure. It pulls it apart. Fusion, you're fusing it together. Okay? All right, let's go to the other side. Here we're given the words. We've got to take the words and put them into a nuclear equation. What is the symbol for radon? Rn. What number is Rn? 86. That number goes on the bottom. Some of them I saw come in, you put it on the top. The mass, the bigger number, goes on the top. 222. Emits. What does that mean?
Gives off.
Gives off. So I'm going to do the arrow. An alpha particle. What is an alpha particle?
42He.
Good. 42He. Two forms. So I'm going to also put a plus. Make sure you put the plus there. That was another thing that I was seeing missing a lot. Polonium. What is polonium? It's 84. And what's the symbol? PO. And what am I going to put on the top here? Well, 222 is equal to 4 plus 218. Done. Okay, I want you to try these two really quickly, and then we'll put them up. I'll put them up so you can see if you're doing it correctly. So go ahead and do the next two. I'm going to freeze this so I can do them at the same time. Ooh, be careful. That one was a little tricky on B. Because it gave me the product first, that's why. So when you're done, look up here, and then I'll know that we're ready to be shown, those two. I don't want to show them until I have most of your eyes up here. So everybody has a chance to do both of them, B and C. Radium is number 88 on the bottom of the S, on the left-hand side. So we're careful on B because they gave you the product first.
Would you add them together? I don't know if I'm doing it right.
Okay, so on the second one, it says radium-230 is produced. So I need to make sure I put radium in the product side because it's produced. When thorium, that's my reactant, emits an alpha particle. Okay, so that one was a little tricky. On the next one, polonium-210 emits, so I'm going to put this emitting an alpha particle, and I get my product. Okay, how many got that correct? Thumbs up. How many got one correct, one off? Thumbs sideways. How many got none correct? Okay, so those of you that got none correct or one correct, where did you go wrong? Where can I help you?
I just messed up.
You just messed up, okay? How can I, is there...
I was adding the alpha and the...
You were adding it to the other. Okay. Be careful. Remember, the key words are emit or decay goes on the product side. Bombard or capture goes on the reactant side. Okay, those are your key words. All right, so then we're going to talk really quickly. If you're still having problems with this when you get to the review assignment, come up and sit with me or have me come help you. Because this isn't hard. You just need to add or subtract. Okay, so why are spent... let me still keep it so you can see those. Why are spent fuel rods removed from the reactor core? What does it mean to be spent? What do you think? It's used. Are they still radioactive?
Yes.
Why do they call them spent?
Because they're all used
Because they take the electron or something like that, and then they like, oh.
What do the rods do, the fuel rods do in a nuclear reactor?
When they're like bouncing around and stuff inside of it, they like bounce onto it and
Emit.
they stay on.
They emit particles that...
They do emit particles, but what is their purpose?
Emergency.
To produce energy, right? So a spent one doesn't produce enough heat to boil the water. That's what a fuel plant, remember, we had to heat the water to produce steam, to turn the turbine. Okay? A spent one doesn't produce enough heat to boil water. It's still producing heat. I can get warm water, but it doesn't produce quite enough. So they're working on taking those spent rods and reprocessing them so that there's ones that are, the parts that are still producing heat will be more concentrated again. Okay? So what do we do with them after they're removed? They're put in a cooling pond. And they're just allowed to just decay. What does alpha particle do to the mass of an unstable neutron or unstable nucleus when it's released? What happens? So think of what's being emitted. What happens to the nucleus? What does it lose? Isn't this an alpha particle? What's being lost from the nucleus?
The alpha particle?
Right. What's in an alpha particle? What's an alpha particle made up of? Helium. But what's a helium made up of?
Elements?
2 protons and
A neutron?
2 neutrons. So I'm losing from the nucleus 2 protons and 2 neutrons. So I'm trying to make it more stable. Okay? By taking those 2 protons off, I'm moving down to a smaller atom. By taking those 2 neutrons off, I'm taking more weight off the atom. Now, the average of being stable for proton to versus neutron ratio, for every 1 proton up until 20, I need 1.5 protons to have a stable atom. After 20, I need a 1 to 2 ratio. Okay? So put in there what you think. Why are they removed? Because they can't boil water. What do they contain? Radioactive isotopes. Didn't give you a lot of room on this one, sorry. What do we do with them after they remove? They're put in a cooling pond. What does the alpha particle do to the unstable nucleus? It takes 2 protons and 2 neutrons. I cannot spell today, sorry. Out. Okay, so before we go on, what does a beta particle do then? Because a beta particle is a 0, -1.
Adds electrons.
So what was that bottom number representing on the nuclear symbol? What does this bottom number represent?
Atomic number.
Atomic number, which is the
Element.
number of,
Isotopes.
no, number of what? Protons, electrons, neutrons?
Neutrons.
Yeah, protons. So if I have a -1 here, I'm actually changing a proton to a neutron. Okay, so on a beta, that bottom number, what's happening at the beta? I'm changing the sign of a proton to a neutron. Okay, so how is an alpha particle represented? Yes, ma'am.
Wait, what does that say?
Can't boil water.
No, the one that said after that.
Cooling pond. Yeah, that's a D. Cooling pond. Okay, so how is an alpha particle represented? We can represent it like this, but more often we represent it like this because we want to know the numbers, right? Okay, how does a beta particle change an unstable nucleus? We just talked about that. Who can tell me? What does it do? We just barely talked about it, guys, less than a minute ago. Yes? Okay, it changes a proton to a neutron. How is a beta particle represented? You should be able to do that. It's either that or 0, -1 e, right? Okay, how is a gamma ray different from an alpha and beta particle? Yeah, it's a 0, 0, and it's a very, very high energy ray. Ray, not a particle. Okay, And how do we represent it? This way or 0, 0 this, but this is the preferred. Whoops. Okay, so at this point, what I'm going to do is I'm going to have you open up your packet, and there is a nuclear review number 4, and I want you to go ahead and use this page and the rest of your notes to do assignment number 4. Next time we'll review electrochem, and then we'll do the electrochem review. And then you should be ready and set for the test. Good to go. If you need help, please come get it. Let's ace this test.